Hi, it's Ryan. I'm going to walk us through the SI questions now for April 29th to May 3rd, the last SI questions that we got. I'm not going to spend a whole ton of time on the reaction mechanisms this go around. I've included them in the notes, but I may incorporate them in the explanations when I think it's super useful for understanding the problem. But anyway, with problem number 1, it says draw the products A, B, and C for the following reaction sequence. So you're starting with an ester and you're reacting it with lithium aluminium hydride. And lithium aluminium hydride is a pretty strong reducing agent. It forms these hydride anions that nucleophilically add to the carbonyl compound and will reduce an ester to a alcohol. So this is the product of that reaction. You've got 2 hydrogens that were added on from the lithium aluminium hydride in this terminal alcohol. So that's product A. And then to product A, you react it with PCC, which is a selective oxidizer. And PCC will oxidize a terminal alcohol or a primary alcohol to an aldehyde, but it won't further oxidize it to a carboxylic acid. So you're left with the aldehyde product right here. And you know, for the purposes of organic chemistry, you can often think that oxidation is the addition of an oxygen bond or the loss of a hydrogen bond, and then reduction is the addition of a hydrogen bond or the loss of an oxygen bond. That's pretty standard. That's not the formal definition for oxidation or reduction, but it's pretty standard in organic chemistry. So that's product B. And then to product B, you react it with this Wittig reagent. And I've included the reaction mechanism for a Wittig reaction in the notes, so I won't exhaust it right here. But I'll suffice it to say that you are exchanging whatever's bonded to your triphenyl phosphine group in your Wittig reagent with the oxygen side of your carbon-oxygen double bond. And so it forms this product where you've added the 2 methyl groups to the carbon-oxygen double bond, and that oxygen has replaced them in the triphenylphosphine, so you get these 2 products. And so that's a Wittig reaction. These are products C, and the reaction mechanism is in the notes if you want to check that out. Okay, so for number 2 is also a Wittig reaction, but I do want to highlight the mechanism in this one because I want you to see what's going on. A lot of this is the precursory reaction to the Wittig reaction, and I think it's kind of important. So you're starting with an alkyl bromide. And so you've got a bromine attached to an R group, and bromine is pretty electronegative, so it's pulling the electron density in that bond away and creating a partially minimally partially positive charge on that carbon, and that's what is attractive to the PPH3. The PPH3 has an extra lone pair of electrons. Let me highlight that right there. And so they're coming in and attacking in an SN2 reaction that carbon. So the bromine is being replaced by the triphenylphosphine. And so that leaves you with this product A right here, where you've got the new bond formed, and then you've also subsequently got a negatively charged bromide anion. And so the P is positively charged because it went from having 3 bonds and 2 extra electrons, 1 lone pair of electrons, so a formal charge of 5 to a formal charge of 4 right here, where it's got 3 bonds and 4 bonds and no pair of electrons. So now it is +1 charged. And so product and then for product A, you're reacting it with butyl lithium, which is an organolithium. Bu stands for butane, and so it's a four carbon organolithium, and it splits up to a positively charged lithium and a negatively charged strong base R group, that butane group. And so the butane group is going to abstract a hydrogen from right here, one of these hydrogens. And then the extra electrons are going to stay on the product A, and then subsequently in that part of the reaction, you are getting or the negatively charged bromine that left is reacting with the positively charged lithium to form a salt. So in product B, you are getting this guy right here, and then so that's a YLIDE. I don't know how to pronounce it, Elide, but it's where a negatively charged atom is right next to a positively charged atom within the same compound. It's similar to a zwitteron, except which is a zwitteron is where there's a positive and a negative charge within the same little molecule, but a YLID or Elide is where that positive and negative charge are right next to each other, and in this case it forms a resonance structure where the negative charge on the carbon can kind of come in and form a double bond with the phosphorus, eliminating the positive charge on the phosphorus and the negative charge on the carbon. So that's kind of the more stable aspect of that resonance structure. And so that is what's going to react with the ketone in the Wittig reaction. And that Wittig reaction occurs just like the one did in the previous example. And so you wind up with this product right here. I'll draw it again up top for clarification. You wind up with this product. And then the product of the Wittig reaction with the oxygen bonded to the phosphorus. You also, I just highlighted it down here, throughout the mechanism, ended up with a lithium bromide salt and butane, from where the butyl group, that negatively charged butyl group, abstracted the hydrogen. So now that's just butane. And so that's number 2, and the Wittig reaction again is in the notes. So number 3 moves from Wittig reactions to the addition of amine groups, and I think the reaction mechanism is important. I included it in the notes for the addition of a primary amine versus a secondary amine, but at the same time, these are pretty standard reactions that you can just kind of follow a trend with. So with the addition of a primary amine group, you're going to essentially replace the oxygen in this carbon-oxygen double bond with the nitrogen to form a product like this. And then, with that methyl group, and then with the addition of a secondary amine, you are going to replace the oxygen with the nitrogen, but the double bond is not going to reform between the oxygen and the nitrogen. Instead, it's going to form adjacent to that bond. So what I mean by that, that's still benzene. What I mean by that is form this product where the double bond forms in an adjacent way, and that's why I think the reaction mechanism is important, because it highlights why this happens. And so I included that in the notes, and I encourage you to check it out. But the carbon-carbon double bond is forced to this side because of these methyl groups. There's not a hydrogen in here. Like right here, I've kind of highlighted that hydrogen. That hydrogen is what's going to be abstracted, and the electrons from it are going to form the carbon-carbon double bond. So in the primary amine addition, for example A, you're forming an imine, and then for the secondary addition, you're forming an amine. And so, this is again pretty standard stuff where the primary amines are going to replace that oxygen in the carbon-carbon double bond, and with the secondary, it's going to replace the oxygen, but the carbon-carbon double bond is going to form adjacent to that carbon-nitrogen bond. But it'll make a lot more sense if you just glance over the reaction mechanism that I included in the notes. So that was 1, 2, and 3, and I'm going to keep going with 4, 5, and 6 in the next video. See you there.